Hi, this is Mr. Yeager looking at the behavior of waves for AP physics. You'll see I also will do a separate one for regular physics as well, because in AP physics we kind of only focus on what mechanical waves will do in terms of when they change densities, when they interfere, and the last one we will mention as well is when they do reflection. So these are the only three behaviors you are interested in as a wave travels toward either another wave or another substance itself. Some of the slides you're about to see have a ton of words on it. I'm going to try to focus on the main ideas in each of those slides. So try to follow along with me, and hopefully it will kind of focus you a little bit better on what really is important with this. So again, we're looking at now what happens when basically a wave interacts with another surface or another wave itself. Okay? So here we go. All right. So the first thing we're interested in is what will happen to the wave when it changes mediums, especially a new density medium. Now, you might hear about refraction. We don't need to do any refraction in AP Physics 1. That's not a topic that's covered. That's covered in AP Physics 2. All right. So we're just looking at going, okay, if this wave is created from one side with this one hand on the left side, the wave's going to move through a less dense and to a more dense medium. What would that mean? Okay. And then vice versa, if it moves from a higher density back down to a lower density, what would happen to the wave? Okay, and again, we're going to look at the main characteristics of wavelength, velocity, and frequency. That's what we pretty much always look at because that's related to the equation. All right, so, all right, what will happen is we do create two types of waves. So this is where you're going to see lots of words, and really all I want to focus on is what do these two words mean? All right. The wave will be both reflected and transmitted through the wave. Okay? So, what happens is part of the wave will go through. That is simply called the, the first one we're talking about here is part of the wave will get reflected. Will bounce back. That is what we call the reflected pulse. So it goes in and reflects back. You might see here, this is kind of an important term, an incident pulse. That's the one that you are creating. So you initially create the incident pulse, and when it hits the boundary, some of that energy will be reflected back. Some of that wave will be reflected back. Again, waves carry energy. Right? What I was about to say first is the rest of that energy will go through. It'll be transmitted. Okay? So basically we have three terms: the incident pulse, the reflected pulse, and the transmitted pulse. Incident's what's created, reflected pulse will bounce back, transmitted pulse will go through. All right. So, what if the second medium is more dense? Now, this is where it gets a little bit, I'm sure people can find some different interpretations of this. When they're saying it's more dense, they're saying it's more massive. Okay? When you travel to a more dense medium, we're looking at it that's more massive, because basically we're saying like the strings are still essentially the same size, same volume, so that the density increases because mass increases. One of the first things to know is that when you have more mass, you decrease the tension. Okay? More mass means decrease in tension. All right? Decrease in tension. All right? And so basically what we're going to look at is we want to know what's the reflected wave going to do, what's the transmitted wave going to do. So the reflected wave, all we need to know is that it's going to be inverted. We can see that in the picture down at the bottom here. We have the incident pulse comes in from the less dense medium. It hits a more dense medium. It's like it hits a wall. Okay? It's something that is thicker. What will happen is a large portion of that will get reflected and actually will invert. Okay? It'll come back from below. All right? And we'll see that when we if you're in class, you'll see that with when we actually start using the big slinkies and everything with that. All right. The transmitted wave will be slower. Okay. The transmitted wave will be slower. Okay. So a decrease in tension will cause a decrease in velocity. All right. So the tension and velocity are directly related. The reason for that is the particles basically aren't as tight together. All right, as we talked about, mechanical waves basically require this medium to travel through, and especially when we get to sound, we're going to learn when the particles are closer together, it'll travel faster. So less tension means they're not necessarily as close and so the velocity will decrease. This, in turn, will decrease the wavelength. The wavelength will shrink, okay? And you can see that right here. All right, this is only a half of a wave, but look at the distance for half of a wavelength and the distance for half of a wavelength. It has gotten smaller. So the thing is, what stays the same? So if I look at my formula, frequency times wavelength, in order for velocity to decrease and wavelengths to decrease, the frequency is going to stay the same. That's pretty clear because the idea is you are the one creating the frequency. How often are you creating those incident waves? You're not going to change. That's not going to affect it, okay? They might not travel as quickly through, but they actually will still be spaced accordingly based on that, the frequency you are using. So the frequency actually stays the same, all right? We'll come back and review all this. I have a separate slide to kind of hit all the main points because this is a lot. We have to relate mass, tension, speed, all right, and wavelength. Mass, tension, speed, and wavelength, all right? And actually, it's not a hard relationship. Everything is directly related except for mass. All right, so here's kind of a quick example showing that. Okay, a quick animation. That'll help out some to obviously see what we're saying. The transmitted wave is the one traveling through the thicker blue line. All right, you can see it's not traveling as fast. It's slowed down. The incident wave, the reflected wave, gets off screen faster than the transmitted wave. All right. Now, if the second medium is less dense, basically now everything's opposite. Okay. That means there's going to be less mass, meaning more tension. Okay, mass and tension are inversely related. Decreased mass, increased tension. All right. First off, that reflected wave, kind of a side note, I feel like, but we have to make sure we understand it. It's not going to be inverted. Okay, that's because it's the thicker material. This is where you're whipping a rope, and then it's connected to a piece of string. Okay. Now again, you might not see that the wave reflected that well. But there should be some little reflection that comes back towards you, and that wave will come back on the same side that it went into the boundary. Okay? Because there's more tension, the pulse will be faster, so increase in velocity, and that'll relate to an increase in wavelength. Again, frequency remains the same. Frequency remains the same. All right? So it's just all about relationships. Again, tension, velocity, and wavelength are all going to work together, and mass is going to be opposite of that. And I'm sure there's going to be some confusion with that. We'll look at a free response. This is actually related to a free response that was used last year, so we'll talk about that some as well. Oops, it skipped on me. All right, so here we go. Here's the main ideas, okay? When you move from low to high tension, okay, so we're looking at low to high tension, okay? The wave will speed up, okay? I'll write all over the side in a second. All right, well, we'll do it together. So, if I increase tension, I'm going to increase velocity, all right? If I increase velocity, I'm going to increase wavelength because frequency stays the same, okay? And if we want to relate back to it, again, mass is inversely related to the tension, so that the mass will actually decrease when you go to the higher tension. One thing we kind of didn't really mention, the amplitude does increase some. All right, we do actually see a higher amplitude. All right, that's because the particles aren't as large, so they're able to basically get moved farther, or a little bit higher in terms of to make sure that obviously the energy stays the same. All right. It's not like there's more energy. That's one thing that everybody always asks me. They're like, amplitude increases, that's more energy. You're talking about a smaller particle, so less mass, all right? And so obviously that energy might be kind of interpreted a little bit differently. Okay? I don't want you to get too confused with that. Energy stays the same. It's more about the fact that those particles are easier to move, and therefore we get a higher amplitude with them. If we're going from high to low tension, all this is opposites. High to low tension, speed decreases, wavelength decreases, amplitude decreases, mass increases. All right? So this would be a page to kind of make sure you, oops, well, it doesn't help when I switch it. This would be a page to make sure that you kind of highlight and go, okay, let me get those relationships related so I can understand how things are changing. Okay? You will get a few questions in terms of high to low density mediums. Okay? there is a formula for velocity and wave tension. This is not on your formula sheet. This is not on your formula sheet. And so, but I have seen in the past, they might ask you to use it, so they would give it to you. So again, you can see that, I mean, it's a kind of a strange formula. I'll rewrite it. Velocity equals the square root of the tension divided by the mass times unit length, okay? So you can immediately see through this, velocity and tension are directly related. Tension increases, velocity increases. They're directly related. We can also see as basically mass increases, velocity is going to decrease, all right? And now that will actually affect the tension as well. This is a strange term, though. We actually have this together. What they're saying is this is the mass per unit length. So if you're thinking about a rope, what they're going to say is for 1 meter, the 1 meter of rope weighs this much or has this much mass. So these are very much a ratio. The M over L is a ratio between the two objects, all right? And that ratio will stay consistent all the way down the rope unless you change mediums. But main thing is, I've seen free responses in the past. You get an answer and they go, okay, now if I say this, I give you this equation, can you explain, can you support your answer with this equation? All right, that's basically what you're going to be looking at sometimes. This is not a formula to memorize. No need to memorize that. All right, you can. There's no rule that you don't, but there's no official. It's not on the formula sheet. All right, and it's something that you could use on free responses, even if they don't give it to you, if you know it. All right, but it's more often that they'll end up giving it to you during the free response question itself. All right. The only other interactions we're interested in is reflection and interference. Okay. So reflection, the key word there is when the wave will bounce off the object, and interference is when the waves will combine. Okay, when the waves combine. Okay. I feel like I missed something there. Just a second. Nope, that's it. All right. So for reflection, basically you just need to know what a wave will do against a fixed and a non-fixed end. All right. This is going to be important for interference. All right. And I'll reset it so you can see the animation. When a wave hits a fixed end, it's going to be inverted. It's going to reflect inverted. It's going to come back the opposite way. All right. So this is going to be something that's going to relate to interference in just a moment. If a wave hits a non-rigid barrier, all right, in other words, the barrier is able to move, all right, the reflected pulse will come back identical to the incident pulse. In other words, it's not going to be inverted. Okay. So let me see if I can reset this for you so you can see it. Okay. So if you look at the top one, reflected wave hits a boundary and comes back and inverted. The top one, you have this little whip up and come back down. That would be a free boundary. It's going to come back exactly the way it came. That's going to be very important. You're going to have to recognize that when we get to this interference stuff next, right here. Okay. So for interference is where the waves combine. All right. When the waves combine. This is again a decent possibility to be a free response for this year. So they love to use interference problems to see whether you understand waves, even though I'm going to guess it actually is going to be a harmonic problem, but we'll see whether that's true or not. Okay? So if two or more waves overlap, they can form an interference pattern. All right? And I think most of you guys have heard of this before. There's two types of interferences. There's constructive interference. This is when the amplitudes are in the same direction. The waves are moving opposite directions, but the crests are on the same side, and they'll overlap each other. And the key things is the resultant amplitude will increase appropriately. All right. So again, you're going to have to be able to, and we're going to practice this, you're going to have to be able to understand how these things approach, combine, and then actually leave afterwards. One thing that I've used to get confused about is it will look like when we do this for a lot of practice, and even outside with the Slinky, it'll look like the waves combine and then basically reflect from each other. What's actually happening is the energy always continues to move in the direction it started. So this wave here is now the wave on the left side. The left wave is now the wave on the right side. They don't come in and reflect back. They combine and then keep going forward. All All right, they never stop. They keep on moving through. The energy keeps on going. But constructive, we're going to have a combination of waves, and we'll get lots of practice with that. Destructive, I keep on skipping things. Destructive interference is the opposite. Sorry, it's pretty light there. This is a link if you actually go to the actual PowerPoint for this, so you can just see an example of destructive interference. This is where you have a crest meets a trough, and they're going to cancel each other out. They don't have to cancel. The amplitude just has to get smaller. They will cancel if they're identical. Okay, identical opposite amplitudes. You will see complete cancellation of that wave itself. But the key thing is the amplitude will get smaller. So don't be surprised where you might get a problem where you have one wave coming in and one wave go underneath. We might say this is 2A and this is negative A. When they combine, what should happen? We should have a smaller wave, but it's going to be up. That's positive A. How do I know that? I simply just add the two together. This negative A is canceling some of the positive 2A, and we should see the result as positive A. What would I see afterwards? I'd see the negative A wave first, and then I'd see the positive 2A second. All right? So that's what we mean by canceling out, combining these two waves for interference. Oh my gosh. All right. So what you're going to be having to be prepared for, and you're going to get plenty of practice. All right. You're going to have to think about what will the interference wave look like when the two waves approach, when they combine, and when they leave. All right. The biggest thing is constructive occurs when the waves are in phase. What we mean by that, I didn't say that the first time, is that they are both in the same direction with each other. Okay. They are basically, you can tell they will combine and become larger. That's the whole idea of in phase. They will be destructive when they're out of phase. That will subtract the two and we'll draw the resultant of it for both of them. And that is pretty much it. All right, thanks.